So before discussing the concept of finding of dA in polar coordinates, we'll first have to understand. We'll first have to visualize a couple of things. Okay, so uh, see the actual derivation part of this is hardly 5 to 10 steps, but to visualize this polar area, that is what you should primarily be focusing on. Okay, so to arrive at the visualization, I would suggest that we go through a set of diagrams, and while you're going through the solution, please make sure you draw these diagrams one time with me, and use pencil and a ruler to draw the first diagram, and for the overlapping ones, make sure you draw using different colors so that things will become very short and concise in your notes. Okay, so first up, we have the variation of theta and the value of x in a circle, which is represented in the Cartesian plane of y and x axis, positive x and negative x, positive y and negative y. Now, for one complete circle, the variation of theta would be, okay, let me say. So let's say this is the base arm, right? And this is how the theta rotates. Okay. If this is the way of rotation, of this theta, what will be the angle rotated for one complete circle? It would be 2 pi. So for the range of theta for one complete circle is theta is equal to 0 to theta is equal to 2 pi. And x here will vary from, let us visualize that as well. So x will vary from minus a to x is equal to plus a. Okay. Now let's see what happens. So we saw what happens for the complete circle. That was part 1. Now let's see half of the complete circle, or for that matter, half of a circle, right? Half of a circle. So we don't have this region here. Okay, now I think I need to be more precise. So let us say for the upper half. Okay, and how does theta varies here? Let's see. So we have the base arm, right? We have the base arm here. Another arm which rotates like this and covers a distance of pi radians. So theta here will vary from theta is equal to 0 to theta is equal to pi instead of 2 pi. Okay, and how will x vary? X will vary from minus a to a. It remains the same. Now let's see what happens in not the complete circle. We need only the quarter of a circle. So for the quarter of a circle, if we assume this to be the base arm and another arm which rotates like this and reaches the quarter, the angle subtended by this rotation is theta is equal to pi by 2 radians, and therefore theta will vary here from 0 to, my bad, from 0 to not 2 pi, this time it would be pi by 2. And how will x vary? Will it be minus a to a? No. X here has to be a to, what is this coordinate over here? This coordinate, let us say this is O, this is A and B. The coordinate of B here would be 0 comma A, and therefore x will vary from A to 0, right? It will vary from A to 0. Therefore x will vary from A to 0. Okay. Now we have quarter of a circle, theta varying from 0 to pi by 2, x varying from 0 to a, and we know that x is equal to r cos theta and y is equal to r sine theta in what representation? In polar coordinates, right? So all the rest of the discussion will be based on this: x equal to r cos theta and y is equal to r sine theta. Now, when I say that this question, the expression dA can be expressed in, the term dA can be expressed in two different phrases. One using polar coordinate, the other using Cartesian coordinate. This is how we, break down the area. So the area represents actually the upper quarter of the positive quarter of the circle. But the same area can be evaluated using two methods. One using polar coordinate, where we have x is equal to r cos theta and we have y is equal to r sine theta, and in Cartesian coordinate where we only have x and y. Now both of these methods have limitations and advantages, and it's always better to understand the derivation of both. So first we'll focus ourselves on polar coordinates. So while using polar coordinates, the first thing to do would be to divide this area into n divisions, okay, and select one area out of this. Which, from when I say select one area, what I mean is consider only this small elemental area, okay, and the one which is highlighted in red color here. Let us name this area as A, B, C, D to be more precise. So this is A, B, and C, D. Okay, so we have A, B, C, D. Now, while you draw this, make sure that AB and CD are straight lines, and AD and BC are not straight lines, they are curves, because that's how we represent a polar curve. Okay, so very important. Now we will isolate out of this complete diagram. We'll isolate only this area and find out certain measurement. Find out the measures of certain sides here. So we'll measure the distance OD and call it as R1, and we'll measure OC as R2. Okay. Now what is DC out of this? DC would be OC minus OD, which is equal to R2 minus R1. Okay. Now, if we consider this curved sides alone, so we have AD and BC. The curve length AD will be equal to OD into angle AOD, which we assume to be delta theta. And why? Because length of the arc is equal to radius into the angle subtended, L is equal to r theta. So arc AD is equal to OD into angle AOD, and arc BC is equal to OC into angle AOD. But what is OD? We have written OD as R2 and OD as R1 and OC as R2. Therefore, we can write that arc AD is equal to R into delta theta, R1 into delta theta, and arc BC is equal to R2 into delta theta. Okay. And we have AB is equal to DC, which we express it as R2 minus R1. Let us say that R2 minus R1 is equal to delta R. Now, why is AB equal to DC? Because if you consider these are concentric circles, right? These are concentric circles, which explains why OA should be equal to OD, and OA should be equal to and YOB should be equal to OC. Okay, now let us bring all these measurements into one diagram. So we have a diagram of an isolated area wherein AB and DC is equal to delta R, and the arc length AD is R1 delta theta, and arc length BC is R2 delta theta. Now comes the most important part of the visualization process here, something that we have learned in limits. We will now assume this area to be as small as possible. Okay, which means we are reducing these dimensions of AD, BC, AB and DC. We are reducing the dimensions. So now we have a new figure, AB, CD. We reduce the dimensions even further, AB, CD. We reduce the dimension even further, AB, CD. So basically we are trying to compress this area. Eventually, as it tends to become very small, what we see is this area ABCD, as it approaches the smallest possible area, smallest area possible, this assumes the shape of what? Shape of a rectangle. Well, ideally we should be saying that assumes the shape of a polygon, and then we'll come to rectangle soon. Now when this happens, we can say that the distance R1, which is OD, maybe better over here, this distance R1 and the distance R2, they are very close to each other, which means that difference should ideally be approximately be equal to 0. So we can say R2 minus R1 approximately is equal to 0. Or in other words, R2 is equal to R1. If R2 is equal to R1, then arc AD, which earlier was equal to R1 into theta, can now be written as R theta, and BC, which was earlier written as R1 into theta, can be now written as R into delta theta. Okay, so now we have a polygon. Right now we have a polygon which has AB and DC, one side equal, one pair of sides equal, and we have AD and BC, the opposite pair side being equal, and all these angles are now 90 degree, and therefore this polygon is a what? Is a rectangle. And the measure of AB and DC is dr. The measure of AD and BC is R delta theta. Now this rectangle will have an area which we will call it as dA, right? And that dA will be area of the region ABCD, which will be area of the rectangle ABCD, which will be length into breadth, which is AB into AD. What is AB? It is delta R. What is AD? Which is R delta theta. So we have delta A is equal to delta R into R delta theta. Now what were we trying to do? We were trying to find out the expression for delta A. Why? Because we were trying to find out this area of the sector. So when we have divided this area into many sections, polar sections, and we found out one value of delta A is equal to delta R into R delta theta, what happens when the number of divisions tends to infinity? What if we divide this entire sector into infinity number of divisions? Then delta A assumes the value of dA, delta R assumes the value of dr, R remains the same, delta theta assumes the value of d theta, which can now be differentiated or integrated, right? So coming back to the discussion one more time. So x bar was equal to integral x sigma dA. X bar was dependent on dA, and now we have derived an expression for dA as equal to R into dr into d theta. So if we try to put this into a nutshell, what we have here is, if we have a function R is equal to f of theta, which is at an inclination theta, equal to alpha, and we have different function r is equal to g of theta, which is at an inclination beta, then the area bounded by these two curves can be written as a is equal to integral alpha to beta d theta into integral f of theta to g of theta, the function f of r comma theta. Now I do understand that some of us are not exposed to this multiple integration, which is slightly above the concept that we learn in class 12th of mathematics, but there's no much actually there's no much complexity. It is just you integrate one function with integrate two functions simultaneously, while you consider one parameter to be the constant. So I don't want to go much into it. We'll see the derivation part. Okay, so if we apply this equation to the given diagram here, we can say that x bar is equal to x into sigma dA. dA is replaced by r into dr into d theta, and since sigma is a constant, I can take sigma to be outside this integrand. Now one integrand here becomes 2. Why? Because we have dr and d theta. Don't worry, this multiple integration is really simple. It is not a tough thing. It's not a challenging thing. So we have two integrands, dr and d theta. We have two limits then. What are the limits? Alpha to beta, right? So it will be alpha 0 to pi by 2. Why? Because this is 0 to pi by 2. And the limits of dr will be, and the limits of dr will be 0 to r. Yes, now this is one point where you may be confused about the visualization. How do we get 0 to r as the limit and that of 0 to pi by 2? Now, if you have watched this solution in detail and if you're breaking it down, and if you genuinely feel that there is a lack of clarity in this limit, make sure you write to me. I'll try to generate an animation or if possible a detailed diagram to explain this concept. Okay, now I really want to do it here, but it's taking along, right? It's taking really long. Even if you watch it in even if you watch it in 2x, it will take you somewhere around 10 minutes. So let's not go much into it. Okay, if the visualization is clear to you, if these limits are clear to you, then what I'll do is I have rewritten the same expression here, with the only difference being that integral dm is written as m. Why? Integral dm is the total mass, which is m. And I have included one new bracket here in the blue color, which means I am integrating only this function x r dr, where I have written as x as r cos theta, and I will integrate only r cos theta into r dr. I'm not integrating d theta here. So I'm integrating only on r cos theta r dr. So cos theta is a function which is dependent on theta, which will be integrated only with d theta, and therefore cos theta is a constant when you consider dr. This is analogous to saying integral y square x dx is actually equal to y square into integral x dx, because when dx is the variable, y is a constant. So we have we have cos theta is a constant now. So cos theta is taken out of the integrand. Cos theta is taken out of the integrand, but it's still within the integrand of cos theta d theta. So what's left inside this bracket is r into r, which is integral 0 to r square dr. Okay. Now, what is r square integral r square dr? It is r cube by 3, limit varying from 0 to r, which is r cube by 3 varying from 0 to r is r cube by 3 minus 0 cube by 3. So what we get is r cube by 3 into cos theta. Now when theta is a function and d theta is the variable, we can say that r is a constant. Therefore I can pull out this r cube by 3 outside the integrand. that becomes r cube by 3 into cos theta d theta integral. What is integral cos theta? It is sine theta. Limit varying from 0 to pi by 2, that becomes sine 90 minus sine 0. What is sine 90? 1. What is sine 0? 0. So what we get is pi r cube by 3m. Now, what is m? Sigma, which is the mass density, is mass by area. Therefore, mass should be equal to sigma into area. Mass should be equal to sigma into area. This area here is quarter of a circle, right? Area is quarter of a circle. Area of the complete circle is pi r4. Therefore, area of a quarter of a circle will be equal to pi r square by 4, which is pi r square by 4 here. M is equal to sigma pi r square by 4. If you introduce this m and replace it in this equation, what do we get? Is sigma r cube into 1, the whole upon 3 into sigma pi r square by 4. So we have pi r cube by 3 into sigma into pi r square by 4. So this becomes r cube by r square is r, sigma by sigma is 1, 1 by pi by 4, pi goes up to the numerator, so that becomes 4r by 3 pi. This is how we get x bar of a quarter of a disk equal to 4r by 3 pi. Now, very similarly, we can also derive the coordinate for y bar as 4r by 3 pi, but this is something I want you to do it on your own. So this time you will find out the limits, you will do the integration, and if you do this integration with me, for one time and try to doing it on your own another time, and then if you give your best for this, for your y bar as well, things will become really clear to you. You will be able to solve a lot of questions on your own, even when a situation arises that you don't know the formula of the figure. All right, so that's it with deriving the polar coordinates. Now we'll do the same for Cartesian coordinates again, which will be something which is based on finding out the Cartesian finding out the limit using finding out the area using multiple integrations. Very simple. So don't try to complicate integration here. Just try to understand the basic steps that have been done. Okay.